where is the classical action in quantum mechanics? So, why is there a formulation where the classical action is fundamental to our understanding of classical mechanics, but where is this classical action actually appearing in quantum mechanics? And so he started elaborating on maybe the first steps towards the construction of a path integral, and this was then picked up by Feynman. And then elaborated this and came to the path integrals, which was before path integrals. That's an alternative formulation of quantum mechanics, quantum mechanics, where now, which now the classical action S plays a fundamental role. So this approach answers in a way the question raised by Dirac earlier, because there the classical action always appears, and actually the classical action always appears as some dimensionless quantity, so dimensionless number, which is dividing the action by h bar. And this means one of, I think, the advantages also of the Feynman path integral formulation of quantum mechanics is that there's always very good visible how the classical world emerges from the quantum mechanics, and this is if the typical action scales. Now the typical action scales of, so we're talking about single particle problems, so you have, in a way, you're asking, you want to construct your propagator in terms of integrals over histories, so trajectories, so you can identify in the sum over trajectories, you can associate to every trajectory particle goes between two space points in some time the classical action. And if this classical action scale associated with a typical with the path, typical path of the particle divided by h bar, so it's much larger than h bar, then you can see how the classical world emerges. And this is quite nice. So if you think of a free particle problem, so the classical action is just a momentum integrated along the trajectory. So in a way, you compare here the typical distance you're interested in, let's say, with the wavelength of the particle. Okay? So this is a very large number. Then you can see how the path integral you're interested in is dominated by specific configurations, and these are those which extremize the action. So you see how the variational principle of classical mechanics comes from some deeper, is there due to some deeper reason, and this is, I mean, immediately there in the path integral approach. And yes, while if A as the typical action scale of some path you're interested in is less of the order of 1, then you're really deep inside the quantum mechanical world. Now, I already said, so path integrals, they will not give you really new results for single particle problems, and even worse, like most of the calculations you do with single particle, with the path integral for the standard textbook problems, they are much more messy and much more complicated, so we will see this as a problem of the free particle, and probably also as a harmonic oscillator. But the motivation is well, it's more efficient once you come to more complicated problems, and also, as I said, so it somehow gives you also an alternative look at quantum mechanics. And I think just said so, modern like condensed matter theorists, I mean, should understand the language of path integrals and field integrals. Then let's just very briefly like say what we are going to look at in the next lecture. So the Feynman path integral approach is all based on representing the propagator of quantum mechanics or matrix elements of the propagator in terms of some high-dimensional integrals. So let me just recall you of the propagator of quantum mechanics. So you know the time evolution of a wave function. This is described by the Schrödinger equation. And looking at this equation, if we take some time-independent Hamiltonian, so if the Hamiltonian would be time-independent, you can also write down some expression, some formal solution, but let's concentrate for simplicity on time-independent Hamiltonians, and I can immediately write down the formal solution of this equation by exponentiating the Hamilton operator. So the wave function at some time t can be given by acting with the exponentiated Hamilton operator multiplied with some scalar, so some time difference t minus t prime divided by h bar. You interact with this on the wave function at time t prime, where here t should be larger than t prime. Okay, so this is just a formal solution to this problem. And what we learn from this is that it might be useful to introduce something like a time evolution operator, which is then also called the propagator. Propagator of quantum mechanics, which is often be abbreviated by Q, the operator, and it tells you the time evolution from time t prime to t, and it's given by well, the exponential operator h bar. And the theta function guaranteeing that we are looking propagation forward in time. Okay, so this is the time evolution operator, and well, it just tells you, I mean, you just see that this time evolution operator stores the entire information on the time evolution of your quantum mechanical systems. So once you understand this object, well, then you know how quantum mechanically system evolves. So this stores this object stores all information on time evolution. Of quantum mechanical systems. So you want to understand this good. And what actually Feynman approach bases on is then to study these matrix elements. So it doesn't have to be matrix elements in the space representation, but often it's convenient to look at the matrix elements in space representation. So this describes a transition amplitude from a system from some state x prime to some state x within a time t minus t prime. Okay? So this is transition amplitudes. So if you understand these for all x and x prime, you can always say, well, the system evolves. And this is like the starting point from Feynman's approach. So he concentrates on these objects. Okay? And the idea of Feynman's approach is to find some alternative representation of this object. So elaborating on the first words of Dirac, Feynman found an alternative representation in terms of some high-dimensional integrals of these transition amplitudes. And how to construct this alternative representation of this matrix element, then we'll discuss in the next lecture, and it will become technical. So, comments, questions? So next lecture is Wednesday, no? On 10 o'clock, and so I don't know, can I maybe see the sheets? So how many people actually, because if it's a small number, then I think we don't have to worry so much about like how to make the exam. So my favorite scheme would be that